Hello everyone. So we are in our fifth tutorial class. In this class, we'll try to understand the plasma kinetics, thermodynamics and excitation in plasma. So I hope this session will be interesting. Plasma parameters, how they are influencing the thermodynamic and transport properties. We have already discussed in our class. I summarize the results over here. So, how it goes? The parameters we are considering here, one is temperature of the plasma, one is pressure that will decide whether the plasma is thermal equilibrium or non-equilibrium. Then thermal non-equilibrium parameter, how it affects the thermodynamic and transport properties, and then finally chemical non-equilibrium, how it is going to affect them. So I come to the first one. What is that? That is temperature. And what we see that as you are increasing the temperature, your ionization is increasing, specificity is increasing, viscosity, the transport property, that is increasing, then thermal and electrical conductivity are also increasing. Basically, all of them are interlinked, because when you are raising the temperature, more and more atoms will be ionized and electrons will be coming into the plasma. So the number density of electrons will increase, number density of ions will increase, and in this process actually naturally it is increasing the specific heat as it is going through the ionization process. And then the thermal and electrical conductivity, both of them depends on the concentration of electrons which are present there. The electrical conductivity is directly related to the concentration of electrons that is present there. For example, argon, when it is neutral, it is not giving any electron for the conduction of electricity. But when it is ionized only, then only it shows that it has significant conductivity. So that is why the electrical conductivity will depend on the number of electrons which are present in the plasma, and that depends on the ionization, and that depends on the temperature of the plasma at which it is operating. Thermal conductivity, of course, the electrons plays a very important role in that. So there are various components in the thermal conductivity. One is heavy species component, one is your electronic component, one is your this reactive component. That reactive thermal conductivity is very interesting, because those conductivity part occurs at particular temperatures, where suppose you are undergoing this dissociation, molecular dissociation, or you are going through the first ionization or going through the second ionization, that time this thermal conductivity peaks. Now regarding pressure, the more the pressure, higher is the collision rate, because the number of entities to collide is per unit volume is more, so collision frequency becomes more. And as we are increasing the pressure, the mean free path is reducing, So that is affecting the whole ionization process and affecting the diffusion also, because while you are going to diffuse, you are colliding more often now. So with pressure, you know that a glow discharge which is occurring, if you keep on increasing the pressure, a time comes when it starts forming arc. Then thermal non-equilibrium, which occurs mostly when you are dealing with plasma at lower pressure. Their electrons being mobile and they are getting much longer mean paper, they can increase their energy compared to the same for the heavy species. So at lower pressure, because of the bulky nature of the heavy species like ions and neutrals, these electrons usually stay at a much higher energy. So this T greater than Th is a very common phenomenon there, and as you keep on increasing the pressure, the transfer of energy from electrons to the heavy species through collision increases. Ultimately, at certain pressure, they equilibrate with each other so that you reach a thermal plasma regime. So, from non-thermal plasma to thermal plasma, the route is just keep on increasing the pressure. A time will come when they will equilibrate. So, you know that the thermal conductivity and your electrical conductivity, which depend on the electron concentration, they will definitely depend on the kind of non-equilibrium which is present there, because the non-equilibrium is influencing the heavy species dynamics as well as the electron species dynamics in a significant way. Similarly, the chemical non-equilibrium, this is due to the flux of the species originating due to gradient in the concentration. So whatever the species concentration you get under thermal equilibrium, that is getting influenced by the additional flux which are coming from the nearby regions. So that flux modifies the density, and that way they modify all the thermodynamic and transport properties, because ultimately at the root they depends on the species concentration and the type of species that is present there. The moment they are influenced, the thermodynamic and transport properties are also influenced. So this is the way the plasma parameters influence the thermodynamic and your transport properties. So now I move to one problem. This is quite interesting problem, because here we are trying to probe a very fundamental aspect in plasma. You have studied in the regular class, but I just want to draw your attention about forming the plasma. If you have plasma, what are there actually? There are electrons and ions, and one is positive and one is negative. The Coulomb force will try to bind them together, and the moment they are joined, they becomes neutral and the plasma is gone. So something you require to keep the plasma in its plasma state so that they do not join together and they stay separated. So what is that? That is the thermal energy. So that is reflected in the kinetic energy of the particles. So if you want to maintain a system in its plasma state, then what you essentially require is that you will be maintaining average kinetic energy of the species or the particles in the plasma much higher than the Coulomb energy for the average distance that is maintained between two particles. So if you want to do that, then if you compare these two and get the values of these two energies, one is your average kinetic energy and another is the average Coulomb energy for a typical separation that is applicable for the plasma. When you compare them, you will be able to see that the average kinetic energy is much greater than the Coulomb energy, and that is why the plasma sustains. Now, in this actually I have taken 4 examples. One is magnetically confined fusion plasma, which is of immense importance as far as the fusion energy is concerned. So there the typical number density is of the order of 10 to the power 20 per meter cube and electron energy of the order of 10 keV. For this we would like to get these two values, that is the average kinetic energy and the average Coulomb energy, that is possible there. Then we have introduced another fusion device, that is inertially confined fusion plasma. So there you get a number density very high, it is more than the density that is available in solid. So there N0 is 10 to the power 31 per meter cube and electron temperature is rather low, it is of the order of 1 keV. For this also we will try to find out these two figures, the average kinetic energy and the average Coulomb energy. Similarly, we will do for space plasma. This is another extreme where you get a number density way below the first two, that is magnetically confined fusion plasma or the inertially confined fusion plasma. The number density is as low as 10 to the power 6 per meter cube, but the electron energy is of the order of 10 electron volt. Now typical lab plasma, laboratory plasma, what we deal with every day, usually you are getting an N0 of the order of 10 to the power 17 per meter cube in low pressure discharge devices and the electron energy of the order of 1 electron volt. So it may be 2 electron volt, 3 electron volt of course, but it is of the order of electron volt only. And number density, typical number density in low pressure plasma of the order of 10 to the power 17, it can reach even up to 10 to the power 19 per meter cube, but typically this is the value. So for these typical plasmas, from one experiment to the other experiment that we have covered here, we would like to understand what is the estimate of these two energies, how they compete. So competition is like that, thermal energy is trying to remove the electron from the atom, whereas the Coulomb attraction is trying to pull them together. So one is trying to disturb the association and one is trying to make the association. So that is the competition between these two. So we will just check in this tutorial who wins. So here I have just formulated the expressions. So for an electron in the thermal equilibrium, the average kinetic energy you all know, it is 3 half kT, and for a singly charged ion attracting an electron, a rough estimate of the Coulomb binding energy is you apply the Coulomb formula. So 1 by 4 pi epsilon 0 Q1 Q2 by R. So R is we are assuming here the lambda d, the Debye length. You have you know that this is the characteristic distance within which the plasma settles itself. So we keep it lambda d, and then E is the electronic charge, and you know the formula of lambda d that depends on the temperature that you are maintaining over there. It is root over of epsilon kT by n square. N is the density. So with these expressions, we will now try to find out what is the value of Ek, the thermal energy, and Ec, the Coulomb energy, and we will try to have a feel of the competition that is existing there. So I have just done those calculations and I have presented that in this table. After calculation, you can do the calculations by your own, and you must do that to really have a feel about these things. So I've just listed it out. So plasma type is magnetically confined fusion plasma. We have listed that it is 10 to the power 20 per meter cube. Inertially confined fusion plasma, it is 10 to the power 31 per meter cube. Space plasma, it is 10 to the power 6, and typical lab plasma, it is 10 to the power 17 per meter cube. And what are the temperatures that you have listed over there? So it was given there the 10 EV, 10 kV, 1 kV, 10 EV, and 1 EV. So that is exactly what is 10 kV, 1 kV, 10 EV, and 1 EV. So we have put over there. Now with these values, the thermal energy, that is Ek, is coming here for magnetically confined fusion plasma is 15,000 electron volts, that is 15 keV kind of thing. And Coulomb energy at your lambda d, it is coming to be around only 0.14 electron volt. So where is 15,000 and where is 0.14? So definitely the thermal energy is winning the competition and it is able to maintain the plasma. Similarly, for inertially confined fusion plasma, what we are seeing that the thermal energy is 1500, that is 1.5 keV, and your Coulomb 1 is only 144 eV. So again you see that the thermal energy is way higher compared to your this thing Coulomb energy at lambda d. So again that allows you to maintain the plasma. Then space plasma, which is the other extreme end, and you are seeing here that it is 10 to the power 6 the number density per meter cube, and electron temperature is 10 eV. There what you are getting that your thermal energy is 15 eV, and your Coulomb energy for the kind of lambda d you are getting, it is 4.5 into 10 to the power minus 7 eV. So the thermal energy is way higher compared to the Coulomb energy here as well. And for lab plasma, you know that the Coulomb energy, this kinetic energy is 1.5 eV around, and the Coulomb energy I have not calculated over here. So it is we need to find it out. So I leave it for you. You can just find it out, and you will see, of course, there that this energy will be much lower compared to your this kinetic energy. Now here one thing is that Coulomb energy, what we are saying here is for lab plasma, the distance that you have to take is definitely the d by length, and for calculation purpose, and you should use the formula 1 by 4 pi epsilon naught E square by lambda d. So you just use that formula and you calculate that, and you just check how much this thermal energy is higher than the Coulomb energy. So I just leave this for you, and I have shown that this one extreme end and the other extreme end, and everywhere the Coulomb, your kinetic energy is much higher compared to the Coulomb energy, and that allows you to maintain the plasma. Now I come to another problem which basically involves the level population in plasma state. This is very much important because you are always making the atoms to excite and de-excite inside plasma, and population of the energy levels are happening as per the Maxwell-Boltzmann distribution. So according to that distribution, what important information we get from this tutorial problem is that if degeneracy of both the level are same, then you cannot get, what is there, the percentage of particles in the higher energy state more than 50% of the of the total population. So you cannot exceed 50% percentage of particles that is in the higher state. It cannot exceed more than 50%. So this problem shows that, but the case when the degeneracy of the upper level is much higher compared to that of the lower level, then it is possible to have more than 50% of the particle in the upper energy state. So that what we will see here. Now this is the Maxwell-Boltzmann distribution. This is U is the energy gap between these two levels A and B. Ga is the degeneracy of the level A and Gb is the degeneracy of the level B, and you are exciting the electrons from B to A. Okay. So Na by Nb, the ratio of population is like this. Ga by Gb we have taken as C and exponential minus U by Kt. So that is the U is the difference. U is the difference in energy between these two states. So what we get, that Na by Nb is equal to this one, and if Ga equal to Gb, then this part C becomes 1 and we get this exponential minus U by Kt directly. Now we just add 1 on both sides. So this is plus 1 and this is plus 1. You take that Na plus Nb goes in the numerator, and here 1 plus U by Kt minus U by Kt goes in the numerator. You just take a reverse of that, inverse it. So it becomes Na by Na plus Nb, and in the top it goes E exponential minus U by Kt, and at the bottom 1 plus exponential minus U by Kt. You just inverted that, and you know that when T is very large, that is what you can do to excite the particles, excite the atoms to the upper energy states. So if you can make even T equal to infinite, you are seeing that this term will be 0 argument and it will be 1 by 1 plus 1. So it is half. So Na by Na plus Nb, whatever temperature you raise, it will be half maximum. It will not cross half. So the ratio of Na by Na plus Nb is not exceeding 0.5, that is 50% of the total population. Now the case when Ga is much greater than Gb. In that case, what is happening? You see that alpha, the ratio of the population, Na by Na plus Nb, that is coming to be exponential of minus U by Kt divided by 1 plus C. So C is this C is here because it is not getting cancelled, because Ga is equal to Jb. What you are saying that Ga is much greater than Gb. Sorry, it will be B actually. Okay. So Ga is much greater than Gb. So in that case, the C is much greater than 1. You should assume, because Ga is much greater than Gb. So C is much greater than 1. And you are getting the expression for alpha, this ratio Na by Na plus Nb is equal to C exponential minus U by Kt divided by 1 plus C exponential minus U by Kt. So now what I advise you, you divide both the numerator and the denominator by C exponential minus U by Kt. So the numerator becomes 1, and in the denominator this one becomes 1 by C exponential of minus U by Kt. So it goes in the numerator, becomes positive, so you get U by Kt, and 1 by C of course is there, and this term gives you 1. So you get this expression. Now as we have already told that if Ga much greater than Gb, then C is much greater than 1. So if C is much greater than 1, and we have raised anyway the temperature very high, So this may become 0, very close to that, and then you get this term as this, because C is very high, this is much smaller compared to 1 which is existing here. So you get almost alpha tends to 1. So that is, you are able to put most of the atoms in the upper energy state only. Okay. So this is possible when Ga is much greater than Gb, but you know that this is not always possible. So you may get a higher population, more than half, 50%, but it may not be 100% as you may expect if C is much greater than 1. So this shows you that the population of the upper energy state, usually if Ga is equal to Gb, is usually 50%, and it may be bit more than 50% if the degeneracy of the upper level is slightly more. Now, where this information is required? Because you know that inside plasma you are always colliding, and through the collisional mechanism you are exciting the atoms to their higher energy state, and at that higher energy state, if it receives some photon or it undergoes some other collision, so that the energy that it receives is more than the ionization energy required from the state to the to reach the continuum, then the atom gets ionized. So at what state they are, it is very much important to know. The other thing is that the diagnostic technique in plasma, this emission spectroscopy always depend on the level population, because higher the energy, more the electrons are excited to the upper states. So more intense is the radiation as they de-excite from the upper state to lower state, and what will be the intensity of radiation, that will depend on the population of the upper state. So that is how many transitions that is happening from that state to the lower state. So they will determine the intensity, and intensity, that's why to some extent is related to the number of what is the temperature, and that is causing the number of electrons that are excited in the upper state. So the intensity is connected with the temperature of the plasma that is there, and this relation what you are seeing here, you see that this upper level population, this is Nb into C exponential minus U by kT. So the population of the upper level is some way is having this factor exponential minus U by kT, and if you are able to take a log of that quantity, then you can see that this minus U by kT comes becomes bare. Okay. So if you plot this quantity, log of this quantity as a function of U, the upper energy state, then you may get a linear behavior with a slope having minus 1 by kT. So that may give you the temperature. So that is why I was telling that it is connected, but the connection is through this exponent. Okay. So with this actually I stop this tutorial, and in the next tutorial we'll be exploring more on this plasma kinetics in the next week. Okay. So for the time being we leave. Thank you.